Ladies and gentlemen, welcome to this SimScale webinar at 6 p.m. Central European Time. And I'm very happy to welcome Noesis Solutions to our webinar as well. And today we have an API webinar talking about Tesla valve design optimization in SimScale. A little bit about SimScale per se. SimScale was founded in 2012 in Munich, Germany. SimScale is the world's first production-ready SaaS application for engineering simulation. And what that basically means is that you can perform CFD, FEA, or thermodynamics simulations inside of your browser. The only thing you need is a decent internet connection and a SimScale account. And with 150,000 users worldwide and more than 300,000 simulation projects, we are the go-to platform for engineering simulation. The agenda for today looks as follows. We'll first introduce Optimus, the tool Optimus, and as well as the Tesla valve use case. We'll then move on to the workflow setup with the SimScale API, Optimus capabilities, and the results we got from there. Before the Q&A session, we will have a demo before we jump to the actual Q&A section. Today, I'm also joined by Anatol Dama, one of my colleagues. And with that, I hand over to my colleague, Anatol.
Thanks, Yusuf, and hi, everyone. I'm Anatol. I'm one of the 5 co-founders at SimScale. I worked for a long time on the backend and infrastructure for SimScale to actually allow our users to run their jobs on SimScale, their simulation jobs. And I am now working in product management, which means that I'm responsible for understanding the demands our users have for our API product. So, for example, we have a SimScale workbench, but we also allow the API to actually integrate SimScale into other products and softwares and workflows. And my job is to understand the kind of features that we want to have for this, and building roadmaps and working with our users to make them successful. And with that, I'm handing over to our guest to introduce herself as well.
Thank you. I'm Ceyhun. I'm one of the application engineers of Noesis Solutions. I have been working with Noesis Solutions since March 2020. I'm mainly answering customers' questions for supporting their projects, which are done in Optimus. My background is mechanical engineering and fluid dynamics, so I'm mostly involved with CFD projects. So we prepared the case study of today with my colleague Sophie, who is the other application engineer of Noesis Solutions. So let me start with introducing Noesis Solutions. Noesis Solutions is a software development company. We are a global team of engineers, developers, and consultants, with the common goal of empowering our customers to develop cutting-edge products with a focus on reducing the time and the efforts of the virtual product development cycle. This is enabled through industry-leading technology for process automation and design space intelligence in a collaborative framework. We offer the best-in-class services for our customers. We have multiple offices and distributors around the globe. We cater to customers in the aerospace and defense, automotive, electronics, industrial equipment, energy, healthcare, and consumer goods industries. No matter your industry, our technologies will help you automate your engineering workflows, explore the design space, and convert simulation results into clear decision metrics. We have 2 products. Optimus is our process integration and design optimization tool. Different CAE software are integrated in, and their operation is automated by Optimus. Today, I will show an example of this process. Ideate is our data analytics tool, which provides a collaborative platform on a browser where several users can work on different or the same data sets to get the most out of their engineering data. And today's case study, a Tesla valve, named after Nikola Tesla, who patented the design in 1920. Tesla valve is a fixed geometry passive check valve. It allows a fluid to flow preferably in one direction more than the other direction. With no moving parts, Tesla valves are popular in microfluidic applications, where the expectation is not really a fully cut flow in one direction, but just a reduced flow rate. Some application examples are seen in medical laboratories, in semiconductor devices, in pulsating pipes, or pulsed jet engines. The performance of a Tesla valve is defined by its diodicity. The name is borrowed from the inspiration of Nikola Tesla's invention, a diode. Diodicity of a Tesla valve is the ratio of pressure losses in forward and reverse flows. The case study we would like to show today is taken from an article on test wall application in pulsating heat pipes. The design suggested by Vries and their team is a modern one with aligned inlet and outlet pipes. So we want to improve the design by varying the four radii shown in the sketch with a fixed inlet pressure in both directions. Here is a sketch of the valve created in the FreeCAD. The design has to be parameterized so that it can be automatically varied in Optimus. So a FreeCAD macro is recorded to change the parametric values into a format compatible with SimScale. And here's the Optimus workflow put together by my colleague Sophie. Each Optimus experiment starts with the geometry creation using the FreeCAD macro. The inlet and outlet boundaries are parameterized based on the text of the CAD file, so the boundary conditions for the forward and reverse flow can easily be alternated in SimScale. So here the upper branch is for the simulation submission for the forward flow, and lower branch is for the simulation submission into SimScale for the reverse flow. We have the inlet total pressure as the boundary condition, which is also defined as a parameter which can be changed directly in Optimus. The SimScale API is based on Python scripts, and here we have 4 of them. The first pair is to start the simulations in SimScale, and the second pair is to extract the results when they are ready. We are extracting the velocity at the outlet section, and in Optimus we are doing the calculations to find the pressure loss starting from the velocities extracted from the SimScale. So from this stage on, the geometry update, job submission to SimScale with this new geometry, and post-processing the outlet velocity is automized. All user has to do is deciding the different geometries for calculations. That can be only one geometry, 10 geometries, or an optimization with an upper limit to the maximum number of evaluations. From the user's perspective, it's only one click to launch simulations to the cloud for several cases and receive the output files. Optimus allows also parallel job submission. Thanks to Optimus Parallel service, one can assign simulations to different nodes at once. Knowing that we have enough core hours in our SimScale account and the simulations are decoupled, which means we don't need to wait for the results of a previous one to start the new one, we can run more than one simulation simultaneously. For that specific case, we decided to submit 8 simulations at once. So each time a simulation is finished on SimScale platform, Optimus will submit a new one to make sure that there are always 8 simulations running in parallel, hence economizing the total time invested for the methods. So the method will be a multi-objective optimization. For this case, we want to calculate a trade-off between a reduced pressure loss for the forward flow and an increased pressure loss for the reverse flow. We ended up in 126 different geometries until a Pareto front was suggested by Optimus. That means 126 times 2 simulations, forward and reverse flow, running on the SimScale platform. The simulations for the nominal case took 39 minutes, where they were still run in parallel. So the simulation for forward and reverse flow were run simultaneously. Total time for a simulation varied between 25 and 60 minutes during the optimization, depending on the mesh size. So if we take an average of 40 minutes for each simulation, it could take up to 164 hours for 126 cases with 2 simulations. So parallel job submission reduced the total time to 1/6. After 28 hours, we had our results for the multi-objective optimization. Here we have a scatter plot for the loss in forward flow and loss in reverse flow for all the cases simulated. This green point corresponds to the initial design. and we want to reduce loss in forward flow, increase loss in reverse flow, and that requirements suggest that those marked points are on the Pareto front. And we observe improvements in both directions at the end of the optimization. And here we have a summary table for the nominal case and 3 selected optimals from the Pareto front. As you see, Optimus already starts with a reduced loss for the forward flow, and it keeps on calculating different optimal points with different weights on the 2 objectives. So in the nominal case, we had around 9% difference between the losses of the forward and reverse flows when they were exposed to the same inlet pressure. And on this Pareto front, if you look at point number 1, this is the optimal design for a reduced loss in forward flow. Point number 2, it's an optimal design for an increased loss in the reverse flow. And point number 3 is our best compromise, which pushes the difference between the 2 designs above 11%, actually. So after deciding that point number 3 is our optimal design, we ran additional simulations to validate it for a catalog value definition of the diodicity. So this time, instead of fixing the inlet pressure, we fixed the inlet flow rate, and we simulated the nominal design and the optimal design, forward and reverse flows, to observe the increase in the diodicity. So for the nominal case, we had a diodicity of 1.69. For the optimal design, we had it up to 1.76, which means almost 4% improvement in the catalog definition of the diodicity for the Tesla valve. And finally, I would like to show you the correlation values post-processing tool of Optimus, which gives a quick view on the impacts of each input on each output. So from this table, one can see that parameter A is the dominating one. It is followed by R, and the radii C is the least dominating parameter. That tells that during the manufacturing process, one should pay attention on the A and R parameters, but a relatively larger tolerance on C will still result in an acceptable design for the Tesla valve optimized. Thank you.
Cool. Great. Thanks, Jaehoon, for the explanation of the workflow, and of course also for the interesting case and the collaboration. It was definitely great to work on this and see the results. Nice. Good. Then, I mean, after we looked at this use case, I actually also wanted to provide some more perspective on what we do with the API. We actually had another use case that we worked on with Noesis a while ago, actually, in the beginning of 21, also on a battery case. And the reason why we picked the Tesla valve case for this webinar is because we also changed the geometry, which was a bit more exciting for us. And just to show you this case as well. This was essentially an application from battery cooling in the automotive space. So actually, this is a battery which is kind of similar to the ones that you would also find in a Tesla electric vehicle. So again, kind of a Tesla case, if you want. Essentially, you can see that we have the coolant inlet here on the left and the outlet on the top right. And the whole point behind the simulation was to basically check for different conditions, the inlet flow rate and also the temperature of the fluid. How hot the battery gets, which is interesting for, of course, safety, but also battery lifetime or battery life expectation. And we also used Optimus again for this, again in a smart way to actually not run a full study across all the different parameter combinations. So we cut down the number of simulations that was necessary from 60 to something like 6 or so. And again, running in parallel, of course, which is one of the nice benefits that you have using SimScale, that you can run jobs in parallel without sort of any performance impact on the negative side, of course. And also cutting then again the simulation time down from 27 hours to something like 4.5 hours. I don't want to go into too much detail on the actual results. The one thing which I want to mention though is that we actually generated these images with our post-processing API. So this is something I also want to mention again later in the roadmap slide, that we are planning this as well. But yeah, so we can actually also generate these images automatically when your study is running. And then to sort of explain what the API can do, or what where we sort of position the API, or where we see the benefits of having API beyond just our existing workbench. Of course, we have the workbench, which is our browser-based sort of software for running simulations, which you saw in the beginning of the webinar that Yusuf showed. All of this is powered by the simulation SimScale cloud platform, which offers, of course, different tools for geometry processing and also for meshing and different solvers. And of course, all of the infrastructure for running your job, storing the results, and so on and so on. I think the one way to explain why we have something like an API, or what the API can be useful for, is to look at sort of the traditional use cases for simulation first. And sort of the very classic use cases, of course, design validation. So you design some product, and before you actually build it, or before you build a prototype that is expensive and takes usually long to build, you actually just want to run a few simulations where you have a very clear idea of what the design looks like already, a clear idea of the boundary conditions and sort of the effects that you want to test and simulate. So you just do this in some graphical application, of course, either desktop application or using SimScale, the SimScale workbench, for example. This is something which is usually very easy to get started. It's very visual, it's very intuitive, and you only do it a few times because you have your design mostly finished already. So that makes total sense, of course. It becomes more interesting if you look at something like iterative design, where maybe you actually want to tweak your design a bit. Maybe you actually want to make a certain number of modifications, which means making changes to design, setting it up again, running a simulation again, looking at the results again. And of course, the more often you do this, the more repetitive the work becomes, and maybe also the more inefficient. One place where this becomes very obvious, if you look at something like design automation. So we simply see across various customers that we have, that they often have similar kinds of problems or similar kinds of designs they create. So for example, in the AEC space, if you look at buildings, they usually build, of course, buildings that look different, but the kind of simulations they want to run on these buildings and the kind of results they expect, the kind of sort of performance criteria they want to check, they're often quite similar. So we often have cases where people sit down and sometimes set up dozens of simulations, just changing the geometry slightly and setting up the same kinds of simulations, looking at the same kinds of results, which is of course very inefficient and not very exciting also for the person setting up all of these simulations. And it can also be error prone if you have to follow a checklist, for example, of creating the same kinds of boundary conditions, the same kind of result criteria and so on. And this is something where it really makes sense to actually automate this. And this is actually where we decided to actually create something like an API, which you can then use to programmatically interface with SimScale, where it's not about you go to your workbench, your SimScale workbench, and manually set up a simulation. We actually write a program and maybe integrate it into existing workflows that you have to actually automatically run simulations and automatically evaluate the results as well. And as soon as you add this API, I mean, there's many more use cases where it just becomes completely obvious that you would never do this in a graphic interface. It makes much more sense if you can couple this to a simulation software. So for example, if you look at generative design, where you create sometimes hundreds of different designs and you want to automatically check how well they perform so you can actually optimize them further, or at some point, of course, get your sort of selection set of the optimal designs that make sense to investigate further. Of course, it doesn't make sense to manually set up these simulations. You want to have a simulation software which you can automatically drive. Then, of course, you have today's use case, which is design optimization. Again, I mean, you saw before how many different simulations we ran. Even sort of being smart about it, it was still, more than 100 simulations evaluating these results. It doesn't make sense to do this manually anymore. What we also have is quite interesting. We have a number of customers who are sort of system or 1D models where they're actually interested in, again, integrating 3D simulation, for example, CFD, into these kinds of system models. And again, in this case, having something like a simulation API, where you can basically just send your model, send a few boundary conditions, and get back your results to integrate and process them again in your system model, is something very useful to have. Where let's say, desktop simulation software or a graphical software doesn't help you much anymore. And the last use case I want to just quickly sort of suggest and maybe also offer some inspiration for Q&A later is digital twin operations. This is something which is also becoming more and more common and interesting for many of our customers, where you put a product out in the world, collect sensor data, and you actually want to see how well does the real product perform in the real world, having real sort of environmental impacts and so on. And there it's again very exciting to collect the sensor data and run automatically simulations to see how the design actually performs, or if there's certain dangers, or maybe design was actually, or the assumptions about the design and its environmental conditions or its operating conditions were just not fully correct. And there it's also very useful to have a cloud-based simulation API where you can just send all of the sensor data, run simulations, and then report back if something is unexpected. I also want to simply, we couldn't resist, me coming from the computer science actually background, couldn't resist to put some code here. So just, we won't go into too much detail, but just to show you for this actual use case that we discussed today, this is how it actually looks like in Python code. So we mentioned before, we have a Python SDK to get you started quickly in developing with our simulation API. We also have one in C#, but just to show you the Python code here a bit, so you can see here on top, you actually create the different boundary conditions. And below you can see how you actually set up the result export. So what kind of results you want to have, how often you want to write them, and so on. So yeah, we think it's quite simple. You can essentially write entire simulation setups in a few hundred lines of code at most. Even if you go into the actual details and tweak every sort of small settings that there exists. But we also of course have templates for common use cases, like of course simulations with our different solvers that we support in SimScale, but also parametric studies. So you can simply take one of these examples and just get started very quickly. And then lastly, I also want to just quickly show you the roadmap. So where are we right now with our API, and what can you expect in the future? So we actually developed this API together with one of our customers in the AEC space, Thornton Tomasetti, who are well known for not just being experts in the actual sort of AEC world, but also actually investing a lot into bringing modern computational tools for architects and designers. So they have invested a lot into this over the last years, have been one of our customers for a while, and they're actually looking into building an integrated app for CAD tools for architects and designers where the architects themselves can actually run wind studies. So they wanted to have something like a wind tunnel app, and for that they needed a simulation API. And we worked together with them on this, and this wind tunnel app was released at the beginning of 2021. So that's something which we found very exciting and very interesting to build. Around the same time, we actually built this first integration with Noesis on this battery case, which was also a very good, let's say, validation of the idea of our API. We are also quite happy about that. Since then, a number of things have happened. So we have a post-processing API in closed beta where you can actually do image and video export, which is also on this battery case. These pictures were actually generated via the API automatically. And we, of course, worked on a number of more cases. So, for example, this Tesla valve case in the meantime. And essentially enabling single region flow simulation with OpenFOAM via our API, which was also used for this specific Tesla valve case. This was all OpenFOAM. Later this year, in the next few months and quarters, we also want to fully release this post-processing API, and also one of our new solvers, a subsonic Cartesian solver, which performs very well and also has meshing integrated. So that's something which we are quite excited about. There's already, let's say, a few webinars being prepared, or a few sort of pilot projects being prepared with this that will also show up in webinars in the next months. So that's that, and the API is available, it's working. It is currently part of our enterprise plan. So we still want to say, if you have an interesting idea for building an app or an integration, or if you want to become a development partner, please contact us. I'm sure we can work something out. So we also put here the link to our Python SDK, so you can check out the code, look at the examples, and get an impression of what it actually looks like. Good, and with that, we're actually done with the sort of, let's say, slide part of this webinar. And I would hand over back to Jaehoon for a quick demo of what the actual workflow looks like in Optimus. So thanks for listening so far.
So this is the workflow in Optimus to submit the testable simulations on SimScale platform. Here's our input deck with the geometrical parameters as inputs and also the inlet pressure as input. We are writing the new values of each input in the FreeCAD macro to create the new geometries. And also, although we didn't use it for this case study, we had the option to change the inlet pressure in the SimScale API. So each simulation could have been run with different input pressures. As an output, we are extracting the velocities at the outlets. we are extracting the vector and we will read the velocity from the last iteration to do the calculations. So we already had a Latin hypercube design of experiment run on this workflow. So for the multi-object optimization, we want to use this Latin hypercube method as the learning population. So I make sure that my fixed parameters are not selected as input variables. I'm switching to the algorithm I want to use in my multi-object optimization. I'm setting my objectives. And I'm defining the starting population. So multi-object optimizer will define a model based on the starting population, and it will guess the candidates for the next population according to this model. After calculation for each population is completed, the model will be updated. So for the next iteration, again, the 16 candidates will be according to the new updated model. Okay, so I started the optimization, and creation of the geometry takes just seconds. So the optimization simulation and the simulations for optimization are immediately submitted to the SimScale platform. So as I said, I will not wait until the end of this simulation. It will take 28 hours if I want to rerun it, but we already showed you the results from a similar optimization method.
Thank you so much, Jaehoon, for this nice presentation. Let me just switch to the Q&A slide deck right now. So if you have any questions right now regarding the presentation, make sure to put them in the chat box and we'll make sure to take some questions now. Well, one of the questions would be directed to both, I guess. Is parallel jobs submission limited to 8? If not, what is the limit there? Maybe that's one for Anatol, I guess, right?
Yep, I can take that one. Yeah, that's a good question, especially because, one reason why we thought it was interesting to actually work together with Noesis and them with SimScale is that one of the promises and features that SimScale offers is basically unlimited scalability, right? So there's a limit, which is very high though. This is just sort of put in place because you should always have limits from a software engineering perspective, but that limit has not been hit. So you can basically go as high as you want from the SimScale perspective. I think just on Noesis side, the typical setup that you do is that you basically, especially if the case is heavily processed, that you only run sort of one job in parallel for a computing core. But I think Jaehoon can say more about that as well.
Yeah, so from our side, the limits will be what makes sense for your algorithm, actually. So for sure, for the specific case, 2 jobs in parallel makes always sense. But for the multi-object optimization we use, the Optimus is learning from 16 populations. So running more than 16 cases at once doesn't really make sense. Optimus will wait only for the 16 populations. But yeah, from the Optimus point of view, it depends on your resources and what your algorithm expects.
Another one, how much CPU hours are spent for one simulation?
Yeah, I can also start on that again. So obviously for many of our customers, cost and an effort for the computation is a concern, or at least interesting to know upfront. Especially if you run such a potentially complex and large study, right? People want to know how much it actually will cost and how long it will take. I think there's like 2 parts to my answer. One answer is actually that before you run a job on SimScale, we can actually provide you an estimate of how long it's going to run and how much it's going to cost. So you get this both in the workbench. So before you start a job in our browser-based workbench, you will actually get a sort of quick pop-up window that shows you how long it's going to run, how much it's going to cost. but you can also get it by the API. So just as it shows up in the workbench, you can also just request information in the API via code, and then, for example, check have automated checks and say, okay, if it's getting too expensive, maybe you want to tweak the setup automatically and reduce the complexity and then run that. So I think in this specific case, the effort was, or the computational effort was not super high. It was something between like 2 and 4 core hours per run or per job, which basically means one CPU running for that amount of time, or multiple CPUs running for the respective small amount of time. And in the end, I mean, for the whole study, this brings you actually to quite low number in the triple digits. So basically something like 100 euros or a bit more than that for the whole study, which I think is pretty nice.
Another question would be, is there a way to estimate the CPU hours to be spent on the simulation a priori?
Yeah, I guess this was part of my previous answer. So yes, there is. So we have multiple ways that we do this. We actually also learn over time, based on the previous simulations that we have seen. So you can actually try this yourself inside the workbench, in our browser-based workbench. Just when you start a simulation job, you actually get this estimate. But yeah, this also works via the API.
We have a lot of technical questions also coming in. Make sure to give us more technical questions. One of my colleagues, Ajit, also joined. He's one of the application engineers here at SimScale. Another one would be, can Tesla valves be used for micro or macro fluidic applications? That's one Ajit can take, I guess.
Sure, that's an interesting question to be honest. I mean, if you actually hear about Tesla valve, we actually think about microfluidics, but there were actually attempts on actually making it to be compatible with the macrofluids also. So, for example, you can use that as a pump in a flow where it can actually generate kind of a pressure loss without any moving parts, again, as we do in the microfluidics. So it's an interesting question. Depends really on the type of application that we actually do. So we do have certain approximations from the Navier-Stokes equation, which correlates with the microfluidics. So I would rather say it can be done, but under certain assumptions. So we need to check on the applications and what kind of results or what kind of optimization we need to do, and then decide whether we can use Tesla valve for those macrofluids.
Another question we have coming in is, would there be a merit to further optimization by replacing circle segments with ellipsis segments?
Yeah, that's an interesting question. I think we had a slide about how relevant are the parameters A, B, R, and D. So those are actually the radii of this Tesla valve that we considered for analysis. And we actually found out that the parameter A and R, which were at the reverse flow mouth of the Tesla valve, which are contributing more to the pressure drop that we actually require. So yes, by changing the ellipse, we are actually changing the radius, and hence, yeah, can actually merit. So this can be actually done as a study to see how much we can actually get a merit out of it.
Perfect. Let's move on. Was this a 2D Tesla valve or 3D?
It was a 2D.
Short and precise. I think that answers it. Does it support supersonic flows? That's a very general question.
I guess it's better for Ajit, right?
Yeah, I could answer. It's really for the low Reynolds number flow. So for supersonic flows, this is gonna actually affect differently. So Tesla valves had never been actually used for supersonic, I guess, until now, but there have been studies. So yes, the answer is yes and no for that. Maybe Sehun can add a little bit on that.
Yeah, I agree. Since it's low Reynolds number, I wouldn't imagine with supersonic flows, and also working fluid for us was water.
Mm-hmm.
So, I mean, at least this simulation was far from being supersonic.
What CAD software is used during the automation?
FreeCAD. We recorded the macro of the FreeCAD. We recorded lines to change the parameters, and we fed it into Optimus.
Yeah, I mean, that being said, we actually have another, let's say, cases, or I mentioned before, we actually doing a number of these sort of pilot projects, and we also connected, for example, to Onshape, which is another nice way to integrate with different CAD software. I mean, in the end, you can basically use any CAD software that you can automate somehow. I mean, for the SimScale API, it doesn't make much difference. So as soon as you can drive your CAD software using software, you can actually integrate it with the SimScale API.
Excellent. We have another question, which is, I missed the first part of the presentation. I was wondering if there's Optimus help running multiple cases at a time, or rather do an AI-based optimization and optimize the parameter we are looking at to get the best cost function we are targeting.
So in Optimus, you have several optimization algorithms. So the one I picked was learning from the previous data to guess the next. I mean, Optimus is always learning from the previous data to offer an optimum solution. What was the second part of the question, I think?
It was if an AI-based optimization is used also for the parameters we're looking at to get the best cost function.
I mean, not the parameters. We define them to be variables, and if they have limited impact on the final result, yes, Optimus stops varying them.
Okay, let's move on to the next one. Can we adjust the type of course to maybe maximize the price-performance ratio, or are we bounded to one type of core?
I'm not sure exactly, but or maybe I'm just not fully understanding the question. But I mean, in general, so I think both Optimus itself has different ways of sort of achieving or optimizing for a certain goal, as far as I know. And then, of course, you can also control this on a higher level with the API integration. But probably it's basically better if you leave it up to Optimus. And there's like multiple ways that you can tweak the optimization process. Maybe that's something that Jayon could say a bit more about. So what kind of different optimization, let's say, workflows there exist.
Yeah, if it's something you can define as an output to your Optimus workflow, you can optimize anything. And since it's multi-objective, it can go with your other objectives.
Yeah. And maybe to also add this, what you could do is you could sort of add in the, maybe this was actually the question, you could, of course, add in the cost estimate into the optimization as well. That's actually something interesting that you could try. We haven't done that so far, especially because in this case it was quite cheap anyway to run. But that would actually be an interesting idea. So maybe that actually addresses the question.
We have a more general question right now. Jobs fail for a lot of reasons, but I have found diagnosis. The issue is extremely trial and error. Mesh sizes, iterations, divergences, model errors, and so on. How are you cleaning this up to pinpoint the causes?
Yep, I can actually give a brief answer to that. At least within SimScale, we do capture every point of the pre-processing, post-processing, and also meshing and simulation. So we do have a lot of validations where we check at the time of import, we check if there is a CAD fault, and then we don't allow the user to move forward with a faulty CAD. So that's how we capture these kind of causes at every stage of the simulation, and that helps us to actually diagnose better.
For the typical optimization process, would 2D flow analysis be used before more refined 3D flow analysis?
Yes, for a proper optimization, we need to switch to 3D analysis from what we learned from those 2D analysis for a complete optimization.
Great. After optimization, what validation technique is used on the final result?
So we made it, for that case, we made it very simple. We ran validation simulations, as I said, trying to simulate the catalog definition of the diodicity. And we observed the improvements also in that case.
Good. Yeah, I think ultimately it depends on the on yourself, right? So you can do anything, right? So you can of course take a final geometry and do validation studies there. Maybe tweak the parameters again a bit. Maybe you actually want to do physical prototyping. Kind of anything that is necessary for your process.
Great. We have a rephrased question regarding the core performance ratio. Can we choose in SimScale a specific type of course like AMD, Intel, or is SimScale only offering one solution? Do you have best practices? What about if the solution requires various computation nodes? How is the latency handled in the cloud? I think that's for Anatol.
Yeah, sure, I can take that one. Yeah, multiple parts of that. So first of all, you cannot directly select the exact kind of machine that you want to run on. We also actually think this is good because most of our customers or most of our end users, we actually want to take this sort of complexity or away from them. It shouldn't, as a simulation engineer, you shouldn't have to make that decision or make that choice. So I think this is one reason why we don't offer this. The second reason is that we can actually offer better price performance by basically choosing from a wide variety of different compute resources that our cloud provider Amazon offers. And based on sort of the past simulation runs that we have done, we can actually sort of pick the hardware that is optimal. So we actually think this is not just sort of a compromise or something that we sort of take away from our users. We actually, I think, provide a lot of value in sort of not exposing that complexity and actually taking care of this ourselves. I think there was a second part to the question, which I already forgot again.
What about if the solution requires various computational nodes? How is the latency handled in the cloud?
Exactly. Yeah. Good question as well. So I mean, so far we actually already years ago we actually tried just experimented and did some pilot studies on sort of doing cluster computing in the cloud, so connecting multiple physical machines together in the cloud and running jobs in them. I mean, this works fine. It's good. I mean, of course, it depends always a bit on the use case, exactly where latencies come to play and what the trade-offs are, and where sort of the break-even point is for that kind of setup. So far, we are simply in the situation that, AWS or our cloud provider provides instances which are so large or machines which are so large that you can run simply, kind of any job you want on them. So for most of these industry relevant problems that we are solving, we simply haven't had the situation where it was extremely necessary to have a large amount of machines connected together. So you don't have to think about latency that much.
That was every question we had so far. If there's no more questions, first of all, thank you so much for participating and asking so many questions. And of course, if you have any more questions, feel free to reach out to Jaehoon or SimScale, Anatol or Ajit or me, and we'll be happy to help you out. If there are no more questions, I think we can close the session. Again, thank you so much for participating. Thank you for also to Jaehoon from Noesis Solutions for presenting today, and also Anatol, as well as Ajit for answering the technical questions.
Great. Thanks, everyone. Thanks for listening.
Thanks.
Thanks,
Bye-bye.
everyone.
Yeah, thanks.